Hi, this is a problem about boxes on slopes. The two boxes in the figure are attached by a massless rope that passes over a frictionless pulley. Box 1 has a mass of 4 kilograms and box 2 has a mass of 2 kilograms, and they slide on frictionless surfaces that make 30 degrees and 60 degrees with the horizontal respectively. To help us visualize this problem, I prepared this sort of visual aid. So imagine that these are the two surfaces right here, and that these are the boxes. So box 2 is mass of 2 and box 1 has a mass of 4 kilograms, so it's a little bit bigger. So imagine that these are the boxes, and this marker right here that's acting as the pulley for me. And as you can see, if box 1 slides down, box 2 slides up, and if box 2 slides down, box 1 slides up, because the rope is transmitting the tension faithfully. So question number A asks, for each box, draw a free body diagram of all the forces exerted on the box and label all the forces and their directions. So to do that, to start with, I'm going to bring my handy physical should be mental note that talks about free body diagrams. And what it says is that in a free body diagram, you represent the object as a point. You take away the environment and leave the effects of the environment. Consider the forces acting on the object or the system of objects that you choose to draw the free body diagram for. And here's a list of forces to consider, and we'll see that when we get to it. And then after that, you're going to pick some axes. You draw the forces that are acting on the body as vectors or vector components emanating from that point that you represented the object by, and then you get ready to solve Newton's second law. So let's follow these guides. First, you represent the object as a point. So I'm going to draw first for box 1. Here's box 1 I'm representing as a point. You take away the environment and leave its effects as forces. So I'm not going to draw anything else other than the forces that are acting on the body. And the list of forces to consider are these forces: the gravitational, the tension, the friction, and other surface forces like the normal force, and O is the other forces that are specified in the problem. So here's my note for the forces. First, I'm going to consider the gravitational force. And just to remind myself, gravitational force is always attractive, always towards the gravitating body. It's always given by Newton's law for universal gravitation. And in the special case that we're on the surface of the Earth or close to it, this gravitational force becomes the weight, which is equal to the mass of the object multiplied by g. And as we've previously calculated, g, the gravitational acceleration due to Earth, is equal to 9.8 meter per second square, and is always vertical. So for my problem, I am near the surface of the Earth, or right on it. So in this case, the gravitational force is going to be the weight, and it's going to be vertical. So for box number 1, this is going to be weight, and it's going to be vertical. So I draw it vertically, and the force due to gravity is going to be equal to whatever the mass of box 1 is, which is 4 kilograms, multiplied by the gravitational acceleration due to Earth, and that's 9.8 meter per second squared. And of course, I'm drawing it emanating from the point that represents the object as a vector. And of course, it's vertical, that is to say that it's pointing towards the center of the Earth. The second force I'm going to consider is the tension force. And in the tension force, the rope is always pulling on the object is always pulling on the rope, and the rope transmits tension faithfully. So that is to say, any tension on the rope on this side is going to be transmitted to the same tension on the box on this side, provided that the pulley has no friction, which is the case. So the tension on box 1 is pulling the box, so it's actually towards the pulley. Okay, it's always pulling on the object. so it's going to be towards the pulley. So that is to say it's going to be in the direction of the slope. So first I'm just going to draw the direction of the slope. That's 30 degrees from the horizontal. So it roughly looks like this. And the tension on box 1 is going to be pointing along the direction of that slope. So that's the force due to tension. Next is the surface forces. First, I'm going to look at the friction and normal forces. So these exist if there are two surfaces in contact. In this case, there are two surfaces in contact. The surface of the box is in contact with the surface that it's sitting on. The normal is always perpendicular to the surface. Okay, so it doesn't matter what direction the surface is. The normal force is always perpendicular to the surface at the point of contact. And the friction force is always parallel to the surface at the point of contact. And the friction always opposes the sliding movement, and it's always proportional to the normal force. So in this case, the slope is at 30 degrees with the horizontal. The normal force is always perpendicular to the surface, and I'm going to draw it emanating from the point representing the object. So this is my normal force. Okay, so just to label them again, this is gravitational. Also in this case, in this special case, it's known as weight, and it's vertical. This is the tension force, which the rope is pulling on box 1, and it's in the direction of the rope. And this is the normal force, and this normal force is always perpendicular to the surface. So I know its direction because I know this makes 30 degrees with the horizontal. Because this surface is frictionless, then there's no friction force. Otherwise, the friction force would be right along the direction of the surface, parallel to the surface. Okay, so that is the free body diagram for box number 1. For box number 2, we can repeat the process again. So I'm going to start with my note for free body diagrams. I'm going to represent the object as a point. And I'm going to take away the environment, but leave only its effect as forces exerted on the body. And here's the list of forces to consider is these forces. And the first one is gravitational force. So just like before with box 1, this box is also going to have a weight that is pointing towards the center of the earth, which is vertical, straight down. And this force due to gravity is always equal to the mass of the object, which in this case, box 2 has a mass of 2 kilograms, and is going to be multiplied by the gravitational acceleration, which is 9.8 meter per second squared. And that's the force due to gravity. The second force that I'm going to consider is the tension force. And in this case, is there a rope pulling on the box? Yes, there is, and it's pulling towards the pulley. Again, the box pulls on the rope, but the rope pulls on the box, so it's going to be pulling up towards the pulley. So I'm just going to draw the slope of the surface, which is going to be 60 degrees with the horizontal, and the tension force is going to be in the direction of that slope. And like I said before, the rope transmits the tension faithfully. So if this tension force on box 1 is equal to T, then the tension force on box 2 is also equal to T, because the rope is transmitting the tension faithfully in this case, because there's no friction on the pulley. Okay, and then the next force to consider after that would be the forces from the surface. That is to say, the friction and the normal forces, because there are two surfaces that are in contact, then these forces will exist. The normal is always perpendicular to the surface, so I'm going to draw that at 90 degrees with the surface, and this is the normal force. There will be friction forces parallel to the surface, but because these surfaces are frictionless, then there is no friction force. So then this is the free body diagram of box 2. And the next thing after considering the forces is I need to pick some x and y axes. And the clever way of picking the x and y axes is such that one of them is along the direction of the motion. That's very good practice, is to pick one of the axes to be along the direction of motion, because that would simplify your equations. But if you didn't do that, the other way of picking it is to pick such that most of your forces are along one of your axes or the other one. In this case, the motion of the box, remember when we showed with the string, is going to be along, sliding up or down along the surface. So it's going to be in this direction, either up or down. And the same for box 1. It's going to be in this direction, either up or down. And the key here is that if I decide that box 1 is moving up, then box 2 has to be moving down. If box 2 is moving up, then box 1 has to be moving down. And the key in this question is to basically, if you can't guess correctly, it doesn't matter. Just pick one of them and it will show from the equations whether you've picked correctly or not. So if I pick, for example, that my box 1 is going to be going up, then I have to say that my box 2 is going to be going down, like this. And if the value of the acceleration comes out to be negative, then I will know that I have made an incorrect assumption, and that just means that the acceleration would have to be in the opposite direction than the one that I picked. So now that I know the direction of motion, I'm going to pick my axes, and the good practice is to pick the axes such that one of them is along the direction of motion. In this case, I'm going to pick, for example, because this is the direction of motion, I'm going to pick this to be my x-axis, and y-axis has to be perpendicular to it with the right-hand rule. And in this case, you could pick either way. You could pick this one to be the x and this one to be the y, or you can pick this one to be the x and this one to be the y. It really doesn't matter, which choice you make. So for example, maybe I'll just pick this to be the x and this to be the y. So in this case, my acceleration is along the y for this box, but it's along the x for this box. It really doesn't matter. You make your choices. Okay? Just for completeness, I'm just going to label the forces here. So this is the gravitational force, which is also known as the weight. And this is the normal force, which is the surface force that responds to the weight of the object on it. And then this is the tension force with which the rope pulls. And the directions, of course, here the gravity is straight down, the tension is in the direction of the slope, the normal is perpendicular to the slope, and here the gravity is straight down, the tension is in the direction of the slope, which is 60 degrees from the horizontal, and the normal is perpendicular to the slope. And that completes part A. Now for part B, the question is determine the magnitude and the direction of the acceleration of box number 1. And to do that, I'm going to have to solve Newton's second law. And just to remind ourselves, here's my physical should be mental note. The Newton's second law says that the acceleration is proportional to the net force and inversely proportional to the mass. And I can do that component-wise in x and y. And to calculate the net force, I could do a vector sum, which I can calculate using the components, and we know how to do that. And I have to decide whether I'm in equilibrium or not based on whether my acceleration is 0 or not. So to do that for box number 1, I look at the forces that are acting on box number 1, and I write down Newton's second law. So first, in the x direction, which I've decided is along the slope, I look at the forces in the x direction. I know that the net component in x is equal to the sum of all the forces in positive minus the sum of all the forces in negative. And in the positive, I have the tension force. And in the negative x, I have the component of the gravitational force that is along this direction of x, the minus x. So that is going to be equal to minus the gravitational force. And if this is 30, then the x is actually the opposite to 30. So I'm going to use sine 30. And it's negative because, of course, it's pointing down. And that is going to be equal to the mass times the acceleration. And we've decided that the direction of the acceleration is along that x, so that's going to be a positive m1 times a. Now, in the y direction, there is no acceleration of the box in the y direction. The box is glued to the surface. It's just moving up and down the slope, but it's not moving perpendicular to the slope at all. So I know that the net force is going to be equal to 0 because there's no acceleration in the y direction. So in the y direction, I have the normal forces pointing along positive y, and the component of the gravitational force is pointing along the minus y. And if 30 is the adjacent angle, then it's going to be the force of gravity multiplied by cosine 30 will give me the y component of the gravitational force, and that, like we said, there is no acceleration, so it's going to be equal to 0. I could do the same thing for box number 2. I could look at the forces in the x direction. And in the x direction, in this case, I decided my x direction was along the normal, so it's the perpendicular to the surface. And in the x direction, the box is not moving. The box 2 is only moving along the direction of the slope, so it's not moving perpendicular to it. So the net force in x is going to be equal to 0. The net force in x is, I have the normal force minus the component of the gravitational force that is along the direction of x, but it's actually along minus x, so it takes a minus sign. And if it makes 60 degrees, if the slope makes 60 degrees with the horizontal, then that means this is 60, this is 60, so cosine 60 will give me the x component. In the y direction, I know that I have the tension force along the positive y, and I know that I have the component of the gravitational force is going to be along minus y. If this is the gravitational force right here, pointing this way, then if I take the component that's along y, is going to be pointing down in the negative y direction. And it's going to be, if this is 60, this is 60, that means this is sine 60 is going to give me the y. Right? If this is 60, then that means this is the opposite to this hypotenuse. So it's the sine that is going to give me this component. And that is going to be equal to the mass times the acceleration, and the mass of box 2 is m2. The acceleration, notice here that the acceleration, because I decided I assumed that this was the direction of the acceleration. If box 1 goes up, box 2 goes down. So its acceleration is actually in the negative y direction, according to my choice of y. So I have to give it a minus sign. So now that I've written Newton's second law, I have two equations that have T and A. So I have two unknowns and two equations. So I can solve that to find out the acceleration. And one way of doing that is this way. I will take this equation 1 and I will isolate T to one side. So that will be equal to the mass times the acceleration plus the force of gravity, sine 30. And if I take equation 2 and also isolate T, then that will be equal to the mass times c minus the acceleration. And then this goes to the other side, so it's the force of gravity multiplied by sine 60. And since the tension is equal to this and equal to the right-hand side here and the right-hand side here, so that means that these two right-hand sides are equal because they're both equal to t. So I can just equate these two, and I find that if I just write it down and I collect all the terms in A, and on the other side collect all the terms that don't have A, then I find that it's 4 plus 2 times A is equal to this piece minus this piece when it goes to the other side. And that tells me that I can calculate A right away, which is equal to this number divided by 6. So that gives me minus 0.44. So notice now that this minus sign, what it's telling me is that my assumption of the direction of the acceleration is the opposite of what's going to happen in reality. So the actual direction is going to be opposite to the direction that I assumed because of this negative sign. So this negative sign indicates that my choice of the direction of A is opposite to what's going to happen in reality. Okay? The other thing I'm going to do once I find out what the acceleration is, then I can plug it in either one of these equations, let's say this one, and I can find out what the tension is, even though I wasn't asked about it in the question, but we're going to need it for the next part, so I'm just going to do that. Take the value of the acceleration that you've calculated and put it as is with its negative sign into this equation, and you'll find the value of the tension to be 17.84 newtons. Now for part C, the question is, if box 2 is displaced by 2 meters, calculate the work done by all the forces acting on box 2. So just remember, these are all the forces acting on box 2. I have tension, gravitational force, and normal force, and I need to calculate the work done by each one of these forces. And remember that the work done by a constant force during some displacement is equal to the magnitude of the force times the magnitude of the displacement times cosine the angle between them. So I am given the magnitude of the displacement. So for each force, I need to find out the magnitude of the force and the angle between the force and the displacement. So to start with, I'll look at, for example, the work of tension. And we've just calculated the value of the tension force. And if I look at the directions of the tension force is along the slope, and the displacement is going to be along the direction that I discovered is the true direction of the acceleration. So now, because I had assumed the opposite, so now I get the correct answer for the acceleration, which means that the actual acceleration of box 1 is going to be down the slope, and for box 2 is going to be up the slope. So that means that the box 2 is going to slide up the slope by 2 meters. So the displacement is actually up the slope. So the tension and the displacement are in the same direction. So that means that the angle between them is 0. So that means cosine 0 is equal to 1. So the work done by tension force is equal to the magnitude of the tension multiplied by the magnitude of the displacement. We've just calculated the magnitude of the tension, so that makes it straightforward to calculate the work done by the tension force. Next, I'm going to look at the work done by the normal force, and you can see right away that the normal force is perpendicular to the displacement. So this is the normal force, and the displacement is up the slope. There's 90 degrees between them, so, and cosine 90 is equal to 0, so that means that the normal force does no work. Next, I'm going to look at the gravitational force, and if you look, you find that the gravitational force and the displacement have an angle between them that looks like this. Gravitational force is down, the displacement is up the slope. If this is 30 degrees, because I've calculated from the geometry of the problem, it makes 60 degrees with the horizontal. That means this is 30. That means this is 180 minus 30. It's 150 degrees. So the angle between the gravitational force and the displacement is 150 degrees. And if you calculate that, cosine 150 degrees is actually a negative number, and you multiply it by the magnitude of the gravitational force, which is mg, multiplied by the magnitude of the displacement, which is 2 meters, you'll get that the work done by the gravitational force is minus 34 joules. And then for the last part of the question, it was just asking about Newton's laws in your own words. And this is how I phrase them in my own words. The first law is, of course, the law that says that nature is fundamentally lazy, that any object at rest or moving with constant velocity tends to maintain that unless compelled by a net force. And the second law says what happens when there is a net force, and that net force, when a net force acts on an object with some mass m, the acceleration of the object is going to be proportional to the net force, that is to say, proportional in magnitude and direction. And the magnitude of the acceleration is going to be inversely proportional to the mass of the object, i.e., the acceleration is the net force divided by the mass. And then, of course, the law number 3 is the action-reaction law. Whenever one object exerts a force on a second object, the second object exerts an oppositely directed force of equal magnitude on the first object. And that concludes this question.